Jai Hind. Myself Dr. Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. So here in this video lecture, we will study the clamper circuits, which is very important with the view of university examinations. So I will tell the concept of the clamper in this video lecture, and we will understand what are the clampers and how they are working. Only one method is required to be understood in a very good manner so that you can perform all the clamper circuit. But just be very careful when I emphasize on a particular sentence. So here the clamper circuit. What are the clamper circuit? The clamper circuit, basically it is not clipping any waveform of the input given. So but whatever input you are giving, whether it's a sinusoidal input or cosine input, whatever input waveform you are giving, so it should not clip that waveform. It has to only clamp that waveform, and it changes basically the DC level of the waveform. Okay, whereas the peak to peak voltage difference should be the same. Always understand the peak to peak voltage of the given waveform is not going to be changed in the output waveform. Let's say the positive peak and negative peaks are at plus 20 and minus 20. The difference is 30 volts. The 30 volts difference will also appear whatever output you are getting at the clamper circuit, right? So only the DC level is going to be shifted, while the clamper circuits, nothing else. And one more important point is the clamping. The clamping is based on the charging and discharging of the capacitor. See, it is consisting of a diode. It is consisting of resistors, and it should have one capacitor, 2 in the circuit for clamping waveform or clamper circuits, right? So the capacitor gets charged and remain on its charging position for getting the output waveform. So this is how you will identify the clamping circuit. Is it should have one capacitor always along with the diode and the resistor, right? Now suppose we should understand more about the clamping circuit. There are 2 types of clamping circuits. First is positive clipper and second one is negative clipper, right? Now the positive clipper circuit, this is the input waveform. This is the input waveform. Okay. So this is the 0 axis. Now this 0 axis, we have clipped the waveform. We have shifted the waveform to the V by V value up. So the whole, this is the negative peak, this is the positive peak. So this is what it is coming out to be 2V, where it is V and this is minus V. So the difference between the 2 peaks is 2V. So we can say that the waveform has been shifted in the positive direction upwards, but the peak to peak difference is always the same. The peak to peak difference is always the same. Similarly, in the negative clipped waveform, the positive is at peak V and the negative is at minus V, so that the difference between 2 is 2V. And here we have shifted the DC level of the waveform downwards. Now this is 0 and this is minus 2V, and the difference between the peak to peak is again to be 2 volts. So the difference, where whatever the clamper is performing, it is just shifting the waveform either in the upward direction or in the downward direction. It is not changing the envelope of the waveform. It is not clipping any portion of the given input waveform, but it is just shifting the DC level either in up direction or in down direction, but upwards or downwards, but the peak to peak difference is always the same. And you can check your answer after doing the clamper numerical. That peak to peak difference should be always same and fixed, right? Now, so how we are going to start the clamping? Always remember 2-3 points which are very necessary to understand. First of all, you have to start the numerical. Now I am emphasizing this particular sentence. You start the numerical from the portion of the input waveform where the diode is forward biased. Okay. Again, I am repeating. You start the numerical from that portion of the waveform, input waveform, where the diode is forward biased, right? And let the capacitor to be get charged. Let the capacitor charged when the diode is forward biased. This is one step you have to perform, and then get the output voltage. Okay. Start the numerical from that input portion of the waveform, input waveform, where the diode is forward biased, and let the capacitor to get charged, right? And then calculate the output waveform, step 1. Step 1 is clear. Again, now you go to that portion of the input waveform where the your diode is in reverse bias condition. Again, I am repeating this and emphasizing this particular sentence, that you go to that portion of the input waveform, where your diode is reverse biased, and the capacitor, don't change the charge on the capacitor, or don't change the voltage on the capacitor. To whatever value the capacitor has been charged in step 1, let the value to remain on the capacitor in the step 2. Okay. You have to take the voltage across the capacitor same as you have calculated in step 1. So step 1 is consisting 2 calculations. First is you will get the capacitor charge or capacitor voltage, and then you calculate the output voltage. Now go to step 2, get the diode reverse biased, and then let the charge on the capacitor or voltage on the capacitor VC to be same on that capacitor. You don't have to discharge the capacitor at all, because in the clamping circuits, while doing the numericals, we consider the capacitor having the time constant to be very large, that it is taking time to get discharged. Although it is not practical at all, but we are considering the same, because we have to get the peak to peak value. Okay, we have to get the peak to peak value. Okay, the capacitor is always assumed to hold the charge while the numerical has not been solved at all. And after the numerical is done, you have got the answer. Then you do whatever you want to do with the capacitor. So your numerical is done. I don't think there is any use that you are going to do anything with the capacitor charge or whatever it is. So let's start one numerical and we will understand what I have just said. Okay. Now it is basic clamping circuit, right? It is a basic clamping circuit. So as I said, this is the input waveform. This is input waveform. square wave input. Okay. This is capacitor in the circuit, right? I have one diode and I have one resistance. Sign conventions are very important. We will take this as plus, this as minus. Output we will take as plus here and minus. For all the numericals, we will follow the same sign conventions of clamper circuit, right? For all the numericals, we will follow the same sign conventions. Okay. Now we will start doing the numerical. Just forget about the capacitor. Forget about the resistance. Just see in this step 1. Step 1. I told you, you have to go to that part of the input waveform where the diode is forward biased. So, this diode for this particular waveform, where the value is always plus V, the diode is what? The diode is forward biased, right? The diode is forward biased. Okay. So, for this positive half cycle, since P is connected to this and N is connected to this, okay, so we have to consider this diode as forward bias. Okay, is it clear? Now, when this diode is forward biased, the capacitor will get charged. Okay. Now, again, when this capacitor is charging, okay. So, what is going to happen? We will take this terminal to be positive and this terminal to be negative. And we will put a voltage VC across it. Right. Now, we will go to the next portion, right? So, here, for the next negative cycle, this diode will get reverse bias. No ways. I told you in the step 1, we have to calculate first VC and then we have to calculate the output voltage VO. Okay. So, this is plus minus VO. Okay. Since this diode is forward bias and resistance is 0. So, voltage across this two terminals will be 0 volts. Okay. The voltage across this resistance will be 0. So, this is one. Now, we have to calculate the VC. So, we will apply KVL in this loop. So, plus VI minus VC is equal to 0. So, VC is equal to plus VI and this is equal to V. So, VC voltage is V and VO is equal to 0 volts. So, my first step is complete now. In the first step, we have to calculate the voltage across the capacitor VC. Okay. When the diode is forward biased and then the output voltage 0. Whatever it is coming, 0 volts in this case. So, output voltage we have calculated and the charge on the capacitor or voltage on the capacitor VC we have calculated. So, we went to that particular cycle where the diode was forward biased in step 1, number 1, and we calculated the VC, the voltage across the capacitor, and then we calculated VO. This is step 1. Step 1 is complete. Now we are moving towards step 2. See, I told you whenever you are moving from step 1 to step 2 for any clamper circuit, you have to take the capacitor charge or capacitor voltage same in the step 2, right? I am going to make the diagram for step 2. Just try to understand. Go to that cycle where the diode is reverse bias. So diode is reverse bias when the voltage is this for the negative cycle. So forget about the capacitor. Just see for this negative cycle the diode is reversing, and we have to get the diode to be in open condition. So this is the step 2 input waveform. Minus V. Sign conventions, make it same. VC we have calculated. V. Diode is open circuit in this case. This we have to calculate, and we should write for step 2, assuming the capacitor voltage to be remained at VC, it is not discharging. Because of time constant tau to be very large. You write too that we are assuming that the capacitor voltage will remain same and it will be as calculated earlier in the step 1, and we are assuming that time constant of the time constant tau of the capacitor is very large, and hence we are not discharging the capacitor at all by the end of our answer comes. Okay, now apply KVL in this loop, because we have the voltage V on the capacitor, polarities are already assigned well. Now we want to calculate VO, output voltage, because ultimately we have to find out the VO. So here VI plus VI minus V minus VO is equal to 0. What is plus VI? My plus VI this time is minus V. So minus V minus V minus VO is equal to 0. So VO is equal to minus 2 V. It is the answer in step 2. Okay. The next is we have to make the waveform. Okay, we have to make the waveform. In case 1 or step 1, the output was 0 volt here. In another step 2, okay, we have assumed this much of conditions, and then calculated our output voltage, applied KVL, and now I am going to make my output voltage waveform VO. So here it is. Step 1, output is 0 volt. Output is 0 volt, right? Okay. And this is minus 2. So here if I want to calculate peak to peak, that is how much? 2V. Peak to peak voltage. In the input waveform 2, as we can see, the peak to peak voltage is 2V. Okay. So this is how we will solve the clamping numericals or clampers. So here again I am going to repeat these steps. Step 1. See. Step 1. Repeat. Step 1. Forward bias, go to forward biased region. Okay. Make the capacitor to be charged. Calculate VC, then calculate VO. Okay, right? Step 2. VC charge remained same on the capacitor. Apply KVL and calculate VO output voltage, and after that make graph for VO. Okay, from here and you make the graph for the output voltage and do the numericals. All the best. Thank you.